Okay, we are in the midst of solving for a rate law expression, and we had determined in the previous video that this experiment was second order with respect to A and third order with respect to B. Now, what we want to do now is determine what the rate constant is at this temperature. Okay, we'll change with temperature. So it's at a specific temperature. Sorry, there we go. Now, you have room in your notes just a little below this chart to do this work if you would like. I wanted to have the data here available to me. Now, you notice that we can pick any rate law. In every one of these, the temperature is constant. It does not matter which one of these you choose to determine the K value. They will all work for this. We can plug in for any one of these. Okay, and if we do that, we know a rate. I'm just going to pick the first one, 4.66 times 10 to the minus fourth is equal to K, that's our unknown, 0.05 squared times 0.05 cubed. Now, if you want to prove it to yourself, you can, that this rate law, that data would have worked, that data would have worked, that data, any one of those would work. Now, if my number is right in my teacher notes here, I have the value 1491. Now, this is one of those times in which units communicate important information. And so we have to put the units in here for K. So let's go on to this next one. Our rate constant was 1491. And to get our units, we take time. So you look up at the experiment and you see it was seconds to the minus 1. The molarity to the minus. Now, the overall order was 2 plus 3 in ours. So we had 2 plus 3 gave us the overall order. It's the sum of the overall orders. And then we take away one of them. Okay, what that does is leaves one molarity so that rate, we still have one molarity factor and we have time in the denominator. Okay, so it's seconds to the minus 1, molarity to the minus 4. Now, it's a little unusual to do this, but we're going to go ahead. The temperature dependent would be rate is equal to 1491. The reason it's temperature dependent is we would get a different K if we changed. Notice in the expression, I don't put numbers in here. I'm putting the symbol and B cubed. All right? So that's one of them. What we can do once we have this is we can solve for new rates. So in this case, we can put in rate is equal to, we know K is 1491. Now, what if we want to change A and change B? Well, we simply put in 6. We know that effect is squared from the rate law expression. We put in 8. And we know that's cubed from the rate law expression. So we can plug in new concentration data and redesign our setup. And we get 2.8 times 10 to the 7th. That would be molarity per second. Okay. Now, let's take a look at the same example. Let's simply look at the factor that things would be changed. So if A is tripled, we put a 3 inside, and then we raise it to the order. Concentration of B is decreased by a half, so we put a 1/2, and we raise it to its power. And what that means is my rate new will equal this factor times my rate old. Okay, so what would happen is each of those rates would change or increase by a factor of 1.125 if you did that algebra. All right, I want to do another example of this. I'll probably work through it pretty quickly, but I think it's important that you see one more example of this before you can attack them in class. So until the next video, this is signing off.